Okay, so I also want to start with thanking the organizers for giving me this opportunity to talk about some of our recent exploration we were doing. So basically this means thanks a lot to Jörg for a very nice introduction to the topic about Rayleigh-Bénard convection. So I'm also going to show some of the data or systems we were working recently. And basically uh, in our attempt to go to higher and higher Rayleigh numbers, which are the basically operating parameters for most natural convective flows, and also to go to lower and lower Prandtl numbers. So as Jörg showed in his initial slide, that Prandtl number is 10 to minus 6 in solar convection. Plasma, we have a solar plasma in outer convective layer. So we want to go to very low Prandtl numbers. So, but let's see how far we can go to understand those kind of systems. So this is a joint work with Katepalli Sreenivasan, Jörg Schumacher, who are here, and Dimitri Krasnov from Technische Universität Ilmenau, whose code have been used to perform simulations at very low Prandtl numbers in extended geometries. So yeah, as you just saw in the last talk, this is solar convection, and it's operating at very high Rayleigh number and very low Prandtl number. And this is on the right, we have convection in Earth's outer core, and it's like planetary magnetic fields are thought to be generated by vigorous convection happening in the outer core, which are basically liquid metals. So Prandtl number, which is ratio of the kinematic viscosity and thermal diffusivity of the fluid, is smaller than unity, much smaller than unity in most of the cases. So it has been observed that convective flows in low Prandtl number, where thermal diffusivity is high or heat diffuses on a faster time scale, is significantly different in terms of scaling laws, in terms of turbulence levels. Like low Prandtl number convection is highly inertial and highly turbulent compared to high Prandtl number convection at the same operating Rayleigh numbers. So it's interesting and intriguing to simulate low Prandtl number convection and to analyze the properties, how they differ compared to convection in high and moderate Prandtl number cases. So yeah, so I'm also going to show the data from Boussinesq Rayleigh-Bénard convection model. For instance, here, if you look, this is a channel of length L, much larger than the depth of the fluid. And if you are not very far from the onset of convection, then a series of like parallel rolls can be observed. This is a real simulation at Rayleigh number of 10 to 5. So we are just 10 times the critical Rayleigh number. And we can see that the hot plumes, they just rise from these locations, and cold plumes, they fall down or they sink towards the bottom plates. So we have a very regular organized structure. And so in this Boussinesq model, we basically assume that the fluid layer is not very thick, or the height of the layer is not very high, very large, and also weak temperature gradient. So so that we can easily neglect the effect of temperature on molecular transport coefficients. And yeah, so basically here's the definition of Prandtl number, Rayleigh number. Prandtl number is nu over kappa, and Rayleigh number is if we have fixed our fluid and geometry or the apparatus, then it's proportional to it's proportional to delta T. It also has the depth of the layer in cube, H cube, so it also depends on H, like depth of the fluid layer. And another parameter, aspect ratio, which is basically the extent of the horizontal extent of the fluid layer relative to the depth, also plays an important role as long as it's not very high. So when you start to constrain the flow, then it can affect the properties. As Jörg also discussed in his slides. So let's look. So we want to go to high and high Rayleigh numbers. So here are some of the experiments. For instance, this is a famous experiment by Nimela, Srini, and other co-workers. So they went up to Rayleigh number of 10 to 17 and observed a nice scaling law, Nusselt number as relative to the nearly 1/3. And yeah, so they used a cylinder of aspect ratio half, and Prandtl number was 0.7 or so. And yeah, we can see that the Prandtl number tends to increase at the end. But as I said, we want to achieve lower and lower Prandtl numbers because of the relevance in natural flows. So let's see what others have done. So this is numerical simulations by Detlef Loss's group. And they also took a cylindrical cell of aspect ratio half. Also, they explored convection in 0.23, like the diameter is 1/4 the depth of the cell. And the Nusselt number, which is, they have plotted normalized Nusselt number, normalized with Rayleigh number to the 1/3. It decreases. That means it's more or less consistent with the 1/3 or 0.3 kind of scaling in low Rayleigh number regime. So for low Prandtl numbers, for instance, this is experiments in mercury, which has Prandtl number of 0.021 roughly. And Glazier and Sano, and co-workers, they performed this experiment in aspect ratio half cell. They also went up to Rayleigh number of 10 to 11, which is highest in this Prandtl number regime. And they also observed that scaling, this Nusselt number follows a Rayleigh number to the 0.27 or some kind of scaling law. So smaller than 1/3. Yeah, some of the experiments, recent experiments by Schindler and Jörg were also involved here. So they also went up to Rayleigh number of 10 to 9 or so in 2 different cells, gamma 1 and gamma half. So again, similar scaling law. And this is aspect ratio 1 cell and numerical simulations by Jörg Schumacher and Janet Scheel. And yeah, so they explored Prandtl number of 0.021 and 0.005, which corresponds to liquid sodium. So as you can see, the maximum Rayleigh number which could be explored is lesser as you go towards lower Prandtl numbers, because fluid is highly inertial, highly turbulent. You have to resolve many like very small time scales, length scales, and it becomes formidable. So then exploiting the fact that Rayleigh number is proportional to h cube, you can basically shrink the horizontal dimension and come up with a slender cylindrical cell. And as Jörg also mentioned this, so they performed this simulation and went up to Rayleigh number of 10 to 15. And you can see that the Nusselt number, which is dimensionless heat transport, is nearly the same. Prandtl number is 1, which corresponds to air or some of the gases. So heat transport does not differ a lot, although Reynolds number, which is the strength of the flow, is suppressed. So this is Prandtl number 1. Now what can we learn from this? Can we generalize this result to low Prandtl numbers? Can we use this kind of geometry to explore low Prandtl number simulations at high and high Rayleigh numbers? So this is one of the motivation. Again, and also we also want to see if we start to rotate this container or cell, because natural convective flows are almost always affected by rotation. So what happens when we start to rotate? So these are the 2 aims of this talk. We will see what happens when we take a low Prandtl number fluid in this slender cell, and what happens when we also start to rotate. So yeah, this is the domain, the same domain which Karthik and co-workers took. And now we have performed simulations between 0.005 Prandtl number and 200. So this corresponds to liquid sodium, and this corresponds to some silicon oils or oils, and we could only reach up to Rayleigh number of 3 times 10 to the 10, which is expected because you are going down in Prandtl number. So we use this NEC 5000 code and perform the simulations, and some of the citations or references are hiding, but it's fine. So since we are performing these simulations in slender cells, we don't know how the properties are modified. So we have to have some references, like so we also took or performed simulations or used the data set which we generated in large aspect ratio boxes, extended boxes, where the effect of side walls are negligible. It's like periodic boundary condition box, although these are closed boxes, but effect of side wall is negligible. So we use this data set, Rayleigh number from 10 to 5 to 10 to 7, and Prandtl number again between 10 to -3 to 7. So in experiments, you can't go to Prandtl number of 10 to -3. Only liquid sodium has 5 times 10 to -3 or so, but in simulations, it's possible. So we will be comparing our like results from the slender cell with the results in this extended square cuboid. Let's see what. Let's look at the flow configuration at low Prandtl numbers. So these are turbulent example of turbulent superstructures at very low Prandtl number. Prandtl number is 10 to -3. Rayleigh number is relatively very high, 10 to 7, and we can see an organized, relatively organized or large scale pattern structure. This is a temperature field, velocity field. We are looking in the mid plane, and if you look, they are relatively well organized. And if you zoom further into these structures, you can see that the variation or typical variation over which, typical length scale over which we have significant temperature variation. In temperature field, it's much larger compared to that in velocity field. Velocity field is highly intermittent and turbulent, whereas temperature field is much more regular at smaller scales. So this is because of very low Prandtl number. We have fast thermal diffusion time scale in this case, and heat diffuses much faster. So we have coarse thermal structures and highly intermittent velocity structures. So these structures are highly decoupled. And yeah, so this is one of the examples of turbulent superstructures. We have studied the properties of these superstructures in somewhat more details in other works. But yeah, and we also looked at the kinetic energy spectrum in the bulk of the flow, because we have like no slip top and bottom walls. So in the boundary layer regions, flow is affected due to walls. But if we move to the mid plane, where the effect of walls can be is nearly negligible, then we can define a spectrum, two-dimensional spectrum. It's wide extended box. So we defined a 2D spectrum of based on the 3 components of the velocity field. And you can see that the spectrum follows the Kolmogorov spectrum very well. We also looked at the anisotropies, and we found that in the bulk region of this extended domain at low Prandtl numbers, the flow is nearly isotropic, very nearly isotropic. And this was also observed by Pankaj Mishra and Mahendra Verma, like long back. For low Prandtl numbers, they performed simulation in pre-slip box and horizontal periodic box, and they found that this is the Rayleigh-Benard convection is Kolmogorov-like. And yeah, so some of the simulations had very high Rayleigh numbers. So basically, low Prandtl number convection, Rayleigh-Benard convection, bulk is Kolmogorov-like. That's what we found. Okay, so let's see the variation with respect to Prandtl number in extended domain. We have zoomed into the flow, and if you change the Prandtl number from 10 to -3 to 0.7 to 7, you can see that the temperature structures become more and more irregular. You can see sharp gradients in the temperature field here, and the velocity field follows the opposite. The velocity field becomes more and more regular on the same scale. So if you look at the flow configuration in the slender cell with varying Prandtl numbers, now we are increasing Prandtl number again from 0.2 to 200. And we can see that if you look at, so these are velocity vertical velocity slice in a like vertical slice, diametrical slice. This is a, so we can see that highly regular, like the small scale fluctuations are suppressed as you increase Prandtl number, and we have smooth, tall structures at large Prandtl numbers, whereas irregular structures in velocity field at low Prandtl numbers. This is not very low, but we have gone up to 0.021, which the results will be shown later shortly. So temperature structure, if you pay attention at the temperature structure, we can see that we have a variety of temperature contours in the low Prandtl number case. So here temperature is nearly 1, and here we have roughly 0, and all kinds of temperature structures or contours are there. But if you look at the high Prandtl number configuration in the slender cell, the bulk of the flow, starting from the boundary layer, is nearly isothermal. And here we have a mean temperature gradient. So this will be clearly seen in the next slide. So basically, we want to understand, is the configuration in slender cell different than in the extended cell or not? And now we want to quantify this. So this is clearly shown by Jörg also in his talk. If you, for instance, here at a given Prandtl number, if you start to increase the Rayleigh number, then bulk of the flow becomes more and more isothermal, well mixed, and you have all the temperature drop within the boundary layer region. Now, if you fix the Rayleigh number and start to decrease the Prandtl number, the opposite happens. Because of large thermal conductivity of the fluid, we have, there is not strong mixing, and temperature can diffuse very quickly in the bulk layer, and we have strong temperature gradients even at Rayleigh number of 10 to 6. So we can see that this red curve, which corresponds to Prandtl number of 10 to minus 3, it has significant temperature gradient. So basically, mean gradient decreases as Prandtl number decreases. Mean gradient in the bulk region, increases as we go down in Prandtl number. Let's look at the slender cell data now. So this is data from Karthik's paper. You have Prandtl number 1, and you are varying Rayleigh number. Now, if you pay attention to the cyan curve here, 10 to 15, Rayleigh number is huge, but there is still a mean temperature gradient in the bulk region. And what happens if you vary the Prandtl number now? So we took data at 3 times 10 to 10, somewhat this data roughly. And if you, so Prandtl number 1 is somewhere here. We have a mean temperature gradient. Now, as you start to increase the Prandtl number, the gradient decreases. And this happens because, what I think, because we have thick, like at low Prandtl numbers, we have thick plumes or thermal structures. And when they pass through the side walls or the rise or sink, they communicate, and there's a net heat transfer in the horizontal direction. So that effectively reduces the, increases the temperature gradient. So we have basically nearly isothermal bulk for Prandtl number 200 or so, but a significant mean temperature gradient at low Prandtl numbers. So configuration is not very similar. At relatively low, so we are still 3 times 10 to 10 in Rayleigh number, and there is a mean temperature gradient. So it's slightly different than the canonical Rayleigh-Bénard model, where the flow is horizontally extended. Let's probe further in the temperature fluctuations. We look at the root mean square temperature fluctuations, and we just subtract the mean temperature, which is still 0.5, it's Boussinesq flow, and we look at the RMS value over the entire domain. It decreases with increasing Prandtl number here, and now we compare directly with data from these extended square cuboid. We can see that the fluctuations TRMS, they have very similar value. And why it's decreasing with increasing Prandtl number, or the opposite? Because the temperature contours, or like thermal structures, they become coarser they occupy larger fraction of the volume. They occupy larger volume in the domain. And since these thermal structures have large temperature anomaly, whether they are cold or hot, when they occupy larger volume of the domain, they contribute larger to the root mean square fluctuations. So that's why we are having this kind of increase with decreasing Prandtl number. Similar effect or similar dependence is observed on Rayleigh number. Here, the data is shown by from experiment in aspect ratio 0.8 cell by Jaya and Robert Eke, and we have Rayleigh number dependence, which also decreases. So theta, like TRMS, root mean square fluctuation, this is in the central region of the cell, not in the entire domain. And this decreases with decreasing Rayleigh number. By the way, we also get Rayleigh number dependence from our data, and TRMS decreases. So basically, the message of this, and here's the data from Sreeni's Nature paper, and theta RMS, or TRMS, sorry, it decreases all the way up to 10 to 15 or so. So this particular characteristic is very similar in the slender cell to that in extended cells. Let's go further and look at the distribution of the temperature, these temperature fluctuations. So we are now looking temperature fluctuations in the bulk region. We are far from the boundary layer. So roughly we exclude 20% in the top and 20% in the bottom. And we look at the middle layer. And we can see that if for low Prandtl numbers, where the fluctuations are distributed as Gaussian roughly. So, or sub-Gaussian in some of the cases. So here dashed curve shows the Gaussian curve. And the higher Prandtl number data in this slender cell shows non-Gaussian or extended or stretched kind of stretched tails. So this was also observed for gamma is equal to 25 data. We analyzed it in this particular paper that the PDF shows very similar behavior with respect to Prandtl number at a given Rayleigh number. This is Rayleigh number of 3 times 10 to 10. Here Rayleigh number is relatively small, 10 to 5, but nevertheless we have roughly the same behavior. And the reason for this stretched tails as we go up in the Prandtl number is again of the low mixing of the high Prandtl number fluid. So time scale is much larger, and the plumes or anomalies, they penetrate into bulk, and they still have large temperature difference compared to the ambient fluid and contribute to the PDF. So why I was saying this, it's because of this. If you look at the entire domain, the PDF, so it's nearly Gaussian for low Prandtl numbers, but as you go higher and higher in Prandtl number, they start to stretch longer and longer. So this is the flatness of temperature fluctuation, the kurtosis or flatness factor. And we can see that for Prandtl numbers up to 20 or so, in the bulk of the cell, the distribution is nearly Gaussian. It has a value of 3. But if you include the boundary layers or regions near the plate, then the deviation starts to appear even at lower than Prandtl number of 1. So I can say that the temperature distribution or like temperature fluctuations are distributed in a similar way in extended domain and also in slender domain. Let's look at the Prandtl number dependence of the heat transport. So as I mentioned, the data in Karthik's paper, so Prandtl number is, heat transport is nearly the same when Prandtl number is 1. We didn't have any significant effect. But what happens if we vary the Prandtl number now? So here is data in gamma is equal to 25 box, extended box. We have, we know that from the simulations and experiments that Nusselt number increases with increasing Prandtl number because of the heat conduction. Fluid becomes more and more heat conductive as Prandtl number decreases. It contributes more to the total heat transport. And Nusselt number is ratio of the total and conductive heat transport, so it decreases with decreasing Prandtl number in the low Prandtl number regime. But the exponent with which it decreases in this regime is nearly 0.2. we observe this kind of scaling for all sorts of Rayleigh numbers, starting from Rayleigh number of 10 to 4 or 10 to 5. Now, if you look at the data in slender cell at different Rayleigh numbers, so here is Rayleigh number 10 to 8 data, 10 to 9, 10 to 10, 3 times 10 to 10. You can see that the heat transport is nearly independent of Prandtl number when it's larger than 1. That's consistent with extended cell data. But at lower than Prandtl number 1, we have a steeper increase in heat transport at lower Rayleigh numbers. And this exponent is indicating this steepness. So we can see that this increases as Prandtl to the 0.6, then it decreases to 0.4, 0.2, and then it nearly saturates to 0.2. So what we can say about the data, as we increase the Rayleigh number, the thermal driving in the slender cell, so at low Rayleigh numbers, the plumes are very thick, the thickness of the structures or anomalies decreases with increasing Rayleigh numbers. So plumes are very thick, and they try to rise or they sink through the slender cell, and then they are not separated far enough, and they can't contribute to the heat transfer. Why I'm saying this? Let's look at this Nusselt number for different Rayleigh numbers. For instance, if you take Rayleigh number 10 to 8 and two different gammas, so gamma 1, this data is taken from Janet Scheel and York Schumacher's paper. So at gamma is equal to 1, means in a cylinder of equal height and diameter, you find Nusselt number which is 19, but in slender cell, the heat transport is only 3. 2.8 to be specific, but it's approximately 3. So it's much smaller than the heat transport in the extended cell, or let's say wider cell. You go at 10 to 9, so we have heat transport of 36, 13 in the 13 in the slender cell. Again, 70, 40. So heat transport is suppressed, but as you can see from this table, it's approaching fast or faster towards the value in the slender cell. So we might expect, for instance, that the heat transport will attain the value in the slender cell. Heat transport in the slender cell will attain the value of that in extended or wider cells when Rayleigh number is high enough. And here is the exponent of this heat transport, Nusselt number as Prandtl to the beta, where beta is the slope of this. You can see that the slope is much higher, whereas if you look at the larger gamma, gamma is equal to 1 or 2 or half data, then slope lies nearly 0.2. So this slope approaches the value in the extended and wider domains as Rayleigh number increases. So we can say that at the small Rayleigh number, lower Rayleigh numbers, the flow, the very peculiar flow at low Prandtl numbers gives very different heat transport values or exponents. But as Rayleigh number is increasing, thermal structures are becoming smaller and smaller, and they are smaller compared to the diameter of the flow, diameter of the domain. Then we basically regain normal kind of convection. So this is Reynolds number, which was also shown by Young. And we can see that the root mean square fluctuation in velocity, it's smaller in slender cell. It's nearly 4 times smaller across all entire Prandtl number range, which we have probed. And here URMS in the in the extended domain. And basically the Reynolds number decreases with Prandtl number. It's known that it decreases with increasing Prandtl number, but the decrease or exponent of this decrease depends on the Prandtl number regime again. For high Prandtl numbers, the decrease is steeper. You have nearly -1 exponent at high Prandtl number regime. So basically this data at slender cell and data in extended domain, they both show this kind of feature. So with respect to velocity scaling, we have similar, basically very similar behavior, both in slender cell and in extended domains, even though the magnitude is different. we probed further and we looked at the PDF of the dissipation rate. So we can see that with decreasing Prandtl number, the turbulent level increases, and we have stretched exponential distribution in the dissipation rates. And also the viscosity times the entropy matches very well with the viscous dissipation in the bulk region of the cell. So these are all sorts of characteristics we just explored. We also calculated the turbulent Prandtl number, which is the effective Prandtl number. It's ratio of the effective viscosity and effective thermal diffusivity in a flow. So in turbulent convection, as Jörg also mentioned, we don't have really a mean flow. So we tried to calculate the turbulent Prandtl number by flux gradient relations, but we couldn't succeed. So we had to use the K epsilon approach, and we computed Prandtl number, turbulent Prandtl number using this particular method. And here we show turbulent Prandtl number in different kind of domains as a function of molecular Prandtl number. We can see that this increases. First of all, the data in slender cell, this data matches very well to the data in extended cell. And even for 2D simulations, we could get nearly the same scaling. So we can see that turbulent Prandtl number is nearly the same between slender and extended domains. So again, the behavior is similar. Like effective Prandtl number in the slender cell is same as the effective Prandtl number in the extended cell. Okay, so now what happens when we introduce rotation in the system in the slender cell? So we solve these equations by introducing rotation, and now additional parameters like the Rossby number and Ekman numbers come into the picture. Rossby number is the ratio of the buoyancy force to the rotation, the effect of rotation basically, and Ekman number is basically rotation time scale, ratio of the rotation time scale and viscous time scales. So this is the parameter space we explored. We took a flow at constant Ekman number. That means we fixed the rotation rate and change the thermal forcing, and we also fixed the thermal forcing and change the rotation rate. So let's look at the flow configuration. This is a flow in Prandtl number 0.021, which corresponds to mercury or liquid gallium. And we can see that when the domain is non-rotating, we have helical flow structure for all Rayleigh number. This is Rayleigh number 10 to 8, 10 to 9, 10 to 10. So we have helical flow structure and three-dimensional character in both in velocity and temperature field. So these are the streamlines of the velocity field, and helical flow structure is apparent. Now what happens when we start to increase? So these are the simulations, or this data is for a fixed rotation rate. Ekman number is 10 to minus 6. It's rapidly rotating flow. And when you start to increase the thermal forcing, you increase driving, then we can see that at low Rayleigh numbers, the rotation dominates the flow characteristics or configuration. We have tall, vertical tall structures connecting the top and bottom plates, but flow becomes increasingly three-dimensional as the thermal forcing increases. So this is again very similar to what have been found in extended domains. So it seems that if we have rotation in the slender cell, we have nearly the same behavior. So this is again increasing rotation strength. Okay, yeah, at the end. So increasing rotation strength for a given Rayleigh number. So yeah, this is non-rotating case. We have three-dimensional temperature and three-dimensional velocity field, but due to Taylor-Proudman constraint with increasing rotation, we have increasingly two-dimensional velocity and temperature field. So here we can see that the velocity fluctuations in the third dimension is strongly suppressed at inverse Rossby number of 30, which is basically high rotation rate. So qualitatively from these flow visualizations, we can say that the effect of rotation on slender cell is very similar to that on extended cells. So this is just the last slide. And if you look at the heat transport, so this is a Prandtl number at 0.021 liquid mercury. Yeah, this is the last slide. So this is heat transport in wider convection cells, gamma half or gamma 1 by data from Glazier and Scheel and Schumacher. And if you look at the data in slender cell, we have anomalous kind of exponent in the Rayleigh number. So Rayleigh number, so Nusselt -1, this is, but Nusselt number increases much faster than Rayleigh to the 1/3. So because as I showed, it's approaching the value in the extended domain. But at high enough Rayleigh numbers, when you are larger than 10 to 9, then the scaling exponent is nearly 1/3. So we are basically in the extended convection regime when Rayleigh number is large enough. And when you add rotation in the system, then heat transport, you can see here, is suppressed in very similar manner to that in extended domains. So the point I wanted to make is that you can take the slender cell and you can go to lower Prandtl number regime, you can add rotation, and you can do all sorts of stuff with which you do with extended domains, and results will be reliable. So thank you so much. This is the summary I have already explained. So thank you so much.
Thank you. Thank you very much. Thank you, Ambrish. So we have time for questions. I have one. Okay, first. No, please go ahead.
Ambrish, you should, at least for low Prandtl number, try to connect the Prandtl and Rayleigh, like Grossman-Lose or your own model. To put them together, there are too many different kind of plots. So I think it's possible to compact some of these plots into scaled plots.
For the non-rotating case or non-rotating event? Non-rotating. Okay, okay. Yeah, like we did earlier. Okay.
No, I mean, I have the same question. I mean, you do not believe there is a pure power law?
Yes.
In principle, right? I mean, not only because of Law's Grossman theory, but I mean, on the basis of simple principles. Right. So is there a way to combine all these plots in a sort of rescaling way such that they collapse on a more or less single course? Or you are telling us that by changing the aspect ratio, every time you have to rescale everything again? I mean, it's...
Okay, so I'm not saying that I will have to rescale everything. As long as we are large, we have large enough Rayleigh numbers. So at low Rayleigh numbers, especially at low Prandtl numbers, the behavior is a little bit anomalous compared to those in wider domains, but not in Prandtl number 1. As in IS, like Karthik's data, we can see that Nusselt number has very similar scaling. But if you have liquid metal in this slender cell, then it shows a different kind of behavior at low thermal driving. But once you achieve some critical thermal driving, it appears from our data, then you are in the same regime as in extended domain. So probably you will have all kinds of exponents which you observe in wider domains. For low Prandtl numbers, the exponent, Nusselt number exponent is around 1/4 or 0.27. For Prandtl number 1 or larger, you will have 1/3 kind of scaling. I hope so. Yeah.
So large Prandtl numbers compact somewhat together, small Prandtl numbers together. There is a possibility of scaling, compacting them together, a low Prandtl number and large Prandtl separately. That's what it looks like. Grossman-Lose and some other work also show that.
So basically, I would say that we will have very similar scalings as we observe in wider domains once we are above some threshold, thermal driving threshold. I'm not sure if it's possible to recombine everything or rescale all the data. Yeah.
Thank you for your talk. So the case with rotation, you have only done in the slender domains, right?
Yes, not in the extended domain. But in extended domains, a group from York Schumacher have done some simulation, but I think the parameter regime is not very similar. So it will be difficult to compare because they didn't go to very low Rossby numbers.
Yeah, because rotation, you were talking about the sun at the beginning, and rotation, just like magnetic fields, tend to impose this preferred direction. And
So there are other complexities. I agree with you. But these are the steps in which the direction in which one could go.
Thank you.
Thank you.
Are there other questions? Well, if not, we can thank all the speakers again. Thank you very much.
Thank you.